Hello? Hello?
Hello.
Good evening, everyone, and welcome to today's webinar on distillation column design using Aspen Hysys. We are Chem Club India Private Limited, and today we are going to learn different concepts on distillation column designing, its interface in the Aspen Hysys, as well as case studies on distillation column and absorber. So before going through today's webinar, we'll go through some of our information like who are we and what we provide to our customers. So we are a process design engineering consultant firm, and we are also providing trainings to different organizations as well as academia students. We are partnered with Aspen Engineering, Aspen Tech, and with the help of their tools, we are equipped with Aspen One engineering suite with which we provide different services for oil and gas refineries, specialty chemicals, as well as the equipment designing, such as heat exchanger design, distillation column designs, and much more. We all are Aspentech certified users having different certifications of basic user certification as well as the expertise certifications with different tools. So we provide trainings on different modules such as developing the simulation model using Aspen Hysys, detailed training on how to develop the simulation models on Aspen Hysys. Similar with the Aspen Plus, advanced process engineering trainings, process control, PSV sizing, Aspen FlareNet, Aspen Hysys Dynamics. Also, we provide the sustainability training like carbon capture, utilization, and storage, as well as the green hydrogen, electrolyzer modeling, trainings. We have detailed curriculum for each of these trainings where with these tools we provide detailed heat exchanger design training, process design and detailed engineering training, distillation column designing, chemical process safety, batch simulations, as well as refinery process simulations. So we have a detailed curriculum on process engineering where you can develop different expertise on understanding on different topics. Having process engineering having 70 hours of training, process simulations having 60 hours of training, Aspen Plus having 30 hours of training, Aspen Hysys having again 30 hours of training, distillation column designing having 20 to 25 hours of training. We have different trainings on different tools, and you can reach us out from our uh, information that we will share. So without further ado, we would like request our trainer to take the stage and go ahead with today's webinar.
Good evening, all. Please mute yourself. And if you have any questions, if you can raise the hand, okay. And if I'm not audible or if you can't audible, so you can write it down in the chat. Okay, so let's start the session. Jatin, can you record the session, please? Okay. Okay, today's session is that using Aspen Hysys, and we'll perform here today how to basic understanding concept of the distillations, as well as we'll take one or two example for the each section like Aspen Hysys as well as distillation column or absorptions. Okay. If you have any question, raise the hand. Okay. And you can ask, or if you want. Okay. So let's start the session. Now everyone available subject is distillation column. So first of all, everyone knows about we are a chemical engineer. We should know the how distillation will work and what is distillation. Now in the distillation, we have a various kinds of distillation are used in industry. Today we are going to learn a simple distillation concept. Okay, and for the simple absorptions, generally everyone knows about the how distillation will work. In a main target and main example of a principle, fundamental principles of the distillation design is a two component. If you want to separate out two component, generally we perform or we'll check the boiling points, right? Volatility concept, vapor pressure concept. These three, four concepts are very important parameter in the distillation of the first stage of the system, right? If you can see here, the Raoult's law is the key component to design the distillation column. Here is a Raoult's law is the ideal conditions like uh, saturation pressure is equal to liquid mole fraction into the partial pressure of the component, right? So generally, this is the ideal concept. If we have a methanol and water, so we can do the distillation design according to this rule. If we have a suppose more pressure, 10, 15, 20, and multiple non-random two liquids are there like ethanol, isopropyl alcohol, and other non-ideal behavior of the system. So we'll add the fluidity and activity coefficient, or we'll develop other kind of thermodynamic system. So first step is whenever we are, why, if you can, you guys, some of the people should know about the how to operate the Aspen Hysys, right? So first page, if you can see, right? So first page is to select the component and thermodynamic property. Okay. So in the thermodynamic property, that is the Pang-Robinson non-random two liquid equations are there. Some of the Raoult's law are there, right? So most of the components generally we prefer and we'll select the thermodynamically, which is as per the guideline and detailed instruction or detailed concept of the distillation column design. So the first concept is a Raoult's law, okay, to select the thermodynamic conditions. According to the Raoult's law and Dalton's law, and basic concept will identify the thermodynamic relative volatility, right? Higher the alpha, easier the separation, fewer the theoretical stage. That rule everyone knows, right? Alpha which is equal to 1 or lesser than 1, separation will not be possible. Alpha always greater than 1, separation will be the possible, but that will be the harder. The theoretical stage will be increases depending upon the alpha. And alpha, which is related to the a partial pressure of the component, okay, of two component, three component, multiple component, okay, and their mole fraction or their boiling point of range. So let's see the some basic fundamentals of the distillation, right? Bubble point, dew point. So the definition is very important when we are searching and when we are developing a curve Txy, Pxy, right? Xy. So we should know the bubble point, dew point. So bubble point, the first drop of liquid converted into the vapor, that's called a bubble point. And same vice versa for the dew point. If it is 100% vapor are there, and if you want to convert to start the condensation, first drop of system, which is called the dew point, right? If we can see simple concept and simple rules are there regarding to the distillation column is PV is equal to nRT, right? So PV is equal to nRT. So pressure increases, always temperature increases, right? Pressure decreases, temperature decreases. So this concept is very important when we are choosing the right option into the distillations, right? Nowadays we have a chat GPT or we have a database of the all the some of the compositions and everything else, right? So we can easily identify the what will be the temperature, pressure, boiling point, and we can check the feed locations and theoretical stage. But suppose if you don't have that much kind of details, right? If you have insufficient detail, if you want to size from the scratch, right? So that will help us to decide the boiling point of the component. Understood? So the whenever we are performing the distillation, we'll check it in the front page of our properties, PXY, PXY. We will check accordingly what will the boiling point, it is azeotrope form or not. Okay. So those criteria need to select or those criteria need to check when we are performing the distillation column. These are the basic steps and points when we performing the distillation column, right? If it is your pillar is strong, then distillation will the design and conceptually will be easy and the right path, right? If you in your mind having the garbage, so definitely output will have been received garbage. Right concept will give you a right answer. Okay. So starting point is after component selection, you need to check a thermodynamically details according to the all perspective. Okay. How the principle, what is the working principle of the distillation column? Now this is the typical sketch of the distillation column, right? We have a column. At the column, we have a reboiler. In the reboiler, vaporize it, vapor and liquid in the two session. Okay. At the bottom, into the reboiler having totally liquid, which called a bubbling liquid. Okay, which called a bubbling liquid. And outlet of the reboiler having a vapor as well as liquid two-phase flow. Okay, when it will be traveling from vapor and liquid, we call it a vapor liquid traffic, right? We call it a hydraulic data of column. Then going into the condenser will condense it receiving reflux pot, and recycle it according to the requirement and purity of the component. Okay. And how the distillation will operate. Distillation having a two section. First is stripping section. Second is rectification section. How you can identify stripping section and rectification section? So based on the feed location. Okay. Based on the feed location, we can identify the how much above the feed location is rectification and below the trays are stripping sections. Assume that if you have a 30 tray and your feed location at 9. So 1 to 9 we called a stripping rectification section. In out of from 10 to below 30, right? 20 theoretical stage, we called a stripping sections. Okay, this is the basic concept of the distillation column. Okay, so the distillation column first, whenever we'll design, we'll perform the shortcut distillation like FUG, French-Ski, Underwood, Gilliland equation. French-Ski equation will give you a n minimum, number of minimum theoretical stage. Underwood equation will give you the minimum reflux ratio, what is Rm, right? And Gilliland equation will shows us a total theoretical stages according to the actual reflux ratio. Now, what is actual reflux ratio? 1.2 time to 1.5 time of R minimum. Okay. We'll see detail into the when we are performing a shortcut distillation. Okay. So understood this basic concept. This concept is very useful when we are designing the distillation column. Right. And one of major equation is feed location. So we have to identify the feed location. According to that, we can identify what is enriching sections and what is stripping sections. This is the basic concept of the distillation column. You have to freeze basic information like first component, then thermodynamic details, and then fourth section is to identify the boiling point of your distillation and pressure, operating temperature, top as well as bottom. Both should be identified in stage of third section. Fourth section, which is having to perform a distillation column sizing. And before going to rigorous sizing, we need to calculate a shortcut method, which is FUG, French-Ski Underwood Gilliland equation, right? That you need to identify the circuit of your as per your requirement. Various kind of circuits are there. This generally circuit which is for more than two component, right? But we have received only one component, two component from the top and rest of the bottom. So our motto and our requirement as per this distillation is to separate any one component out of 2, 3, 4, 5 component. Okay, this is the rigorous distillation. You can also having, you can take it, suppose if you are feeding 4 to 5 component, also you can strip out from about 2 to 3 component, rest of the 2 component or 2 to 3 component from the bottom, right? But if you are performing an ADU VDU like crude oil distillation, that will have a separate concept and fundamentals for that. But fundamentals and whatever we are saying like selection, thermodynamic property, concept, relative volatility, and everything has to be the same, right? But different in the conceptually or different into the what we can say diagrammatically. In the ADU video, we have to take it from the side stream. Okay, this is the simple structure of the distillation column. Okay. Now, fractional distillation, as we seen, a different but relatively close to boiling point. So generally, relative volatility is a partial pressure of component A divided by partial pressure of component B. Right? Suppose I am taking benzene plus toluene. Okay, in the benzene plus toluene, right? We have to identify what will be the partial pressure of 80 degree or boiling point range. What would be the benzene partial pressure, and same for the temperature or same for the toluene partial pressure. Suppose I am feeding 0.5, both of the in distillation column. So what is the target to identify? First, I'll target it uh, boiling point range. What is the boiling point between the 0.5, benzene is 0.5 and toluene is 0.5. That boiling point range gives us to evaporate or to vaporize the benzene from the solutions, right? And boiling point, according to the boiling point, say 93.6 is my boiling point. So according to 93.6, I wanted to identify what will be the partial pressure of the benzene and what is the partial pressure of the toluene. And that the average, I'll identify the relative volatility. Okay, same thing. This fundamental will not be changed at any kind of distillation column. This is the most conceptual, powerful concept when we are designing distillation column. Right? If we are using crude oil, benzene toluene separation, air separation, solvent purification, concept will be the same. Okay, that we need to identify. Second thing is vacuum distillation. Suppose the vacuum distillation used to separate high boiling or sensitive component, we are using our vacuum distillation, right? Vacuum distillation will take up the pressure below atmosphere. So obviously, previously I explained the concept PV is equal to nRT. So this ideal law will help you out. Pressure decreases, so temperature decreases. So P is directly proportional to the temperature. So vaporizations according to this set based on the operating condition. And this one is the very critical task when we are designing distillation column. Because initially we have to freeze operating temperature of the bottom, top, and operating pressure of the column. Same operating temperature of the bottom as well as operating pressure of the bottom. These four things are very important. Across the operating pressure, the delta P we need to consider. This delta P is also very important when we are sizing the distillation column. That will be considered in the next part. Okay.
Kaso betray ko.
And then again, the steam distillation. So this steam distillation is a direct distillation of the system. Assume that this is the pot, right? In the pot, having the two liquids are there, right? And in the pots, we are purging directly steam. And steam
Sorry to interfere.
will change,
We should also.
will change the
Hello?
system, will change the latent heat
Kekada.
of the system. Then we can evaporate a two composition. Like first is steam or with water, and second theme is whatever we want to evaporate or solvent, right? So this heat sensitive material, we are not going to heat multiple time and very high temperature. Okay, so we'll avoid to destroy or decompose the material or to what I mean to say, the aroma of the component, to maintain the aroma of the component. So we perform the steam distillation, right? So since steam distillation will maintain the aroma of the component like toluene water, right? So toluene will maintain their aroma and will not be decomposed. We can give you, we can give us a maximum output as compared to the indirect heating, right? That is the water insoluble component. So that will be the very helpful us to do perform the steam distillation. Okay. Generally, will this kind of steam distillation will be used and performed into the essential oils like mainly perfumery industry because we maintain good aroma in that case. Okay. Then pharmaceutical product. Okay. Then food flavors. So those are the useful of steam distillation in this kind of industry. Okay. Second thing is other type of distillation is extractive distillation. The extractive distillation mixture with the very close boiling point or a low relative volatility. So we'll add the entrainer example. Suppose ethanol plus water having performing 88% and 12% azeotrope. So now we wanted to know what entrainer will be used. So cyclohexane is a good option. Cyclohexane soluble with the water, but not soluble with the ethanol, right? So whenever we are performing distillation design, so we'll evaporate from the top to add here as a third component as a cyclohexane, and ethanol we can get it 100% pure, and bottom we can get it in water as well as cyclohexane. Then we can separate out in the separate distillation column to separate the water and cyclohexane, and again cyclohexane will reuse to separate out ethanol and water, right? The concept, relative volatility concept, everything concept is the same. Okay, so this is the best examples for the separations of the ethanol water. Okay, to use the cyclohexane. We have other kind of example too, like benzene cyclohexanes. Also, we can separate out it from the ethanol. Suppose if you have a ethanol benzene cyclohexane, and the ethanol and benzene is a mixable like a water, so you can add a cyclohexane, right? So this is the distillations of the for the azeotropic distillation. Second thing is reactive distillation. So reactive distillation perform the reaction inside the distillations, right? So if you can see here, the reaction products are continuously removed by the distillations. Okay, the reaction is driven towards the high conversion, improving the overall efficiency of the process. So combining reaction, separation, one unit reduce the number of equipment required, lower energy consumptions, simplified overall process designs. Okay, make in reactive distillation economic choice for many industrial applications. So here is a principle. I am not saying 100%. Okay, you can reduce your examples, or you can reduce your. We can reduce our equipments and required equipments, but definitely that will help us. And this is a special kind of distillation which is performed, like specifically generally this kind of distillation will perform into the when chemical industry, agrochemical, fertilizer industries. Okay, the petrochemical, oil and gas will not be performed. In that case, we have a simple distillation. We have seen already azeotrope distillations by using the entrainer. So here is a basic complex of the separations. Why distillation is required for the simulations, right? So simulation we use for the multi-component mixture that will be reduce our time. Okay, we'll design this column within a 1 or 2 days instead of doing the manual calculations. Okay, you can also perform the complex separations, accurate thermodynamic properties such as Pang Robinson, RTL, SRK, Unique acids, depending upon the requirements. Okay, we have a multiple options to select the thermodynamic models according to our requirement. Okay, so then column design and performance such as parameter like number of tray, feed location, reflux, condenser duty, reboiler duty, right? So in general, in the totality, I would like to say, if you can use the simulation, that will be reduce efforts, times, and everything. And simulation also guide you when you are taking the concept sensitivity analysis, design specs, optimizer, right? In that case, at that time, right? So they will guide you to the exact column output, right? We have a certain limitation of the knowledge. If we forgot some concept, okay? So software and distillation having a some what I mean to say options. If you can select, if you can provide the design spec sensitivity analysis, so column will optimize by their own way by using the concept. Means suppose if you can design choosing the design specs of sensitivity analysis, column automatically will guide you to take it or you can choose this reflux, this temperature or this stage or this dia, anything else. Okay, after running the column, you should ask the simulation software to optimize the column. That's called the sensitivity analysis. That's called the design specs, calculator, optimizations. Everything is to be there. Then process optimizations. Also, you can do it by using sensitivity like temperature, pressure, fluid location, compositions. All should be you can identify. Okay, that's why we are using process simulator nowadays. So specifically, we are talking about the Aspen series. Okay, in the Aspen series, having Aspen Plus, which is used chemical, agrochemicals, fertilizers, all kind of petrochemical, refinery, oil and gas, pharmaceutical, solids, everything. Aspen Plus is a multi-purpose simulator. Hysys generally we specify or select according to the petrochemical, oil and gas, fertilizer, or some which is details or data available into the Aspen Hysys literature or database. And various softwares are there, but Plus, which is one of the best software to perform any kind of distillation. And this, whatever, if you are seeing the graphics, right? Whatever you are seeing, this is the Aspen Plus graphics. Okay. Now, what is shortcut distillations and rigorous distillations? Shortcut distillation, as I told you, will use the FUG method, French-Underwood-Gilland equation method. Okay. In that case, we identify the number of stage, reflux ratio, feed stage, total theoretical stage, little bit of duty, top temperature, bottom temperature, top condenser duty, reboiler duty, then flow rates. So that will be calculated by the shortcut distillation. Now, what rigorous distillation will perform? Rigorous distillation will perform stage by stage calculation, like distance between or calculating between one or two tray. In each tray, they will give you vapor liquid traffic data, right? In the vapor liquid traffic data, what details you want. So that will the detail like the density of the vapor, then flow rate of the vapor, right? Then viscosity of the vapor, volumetric flow rate of the vapor. Same for the liquid. Now, main concept of the distillation for the when we are selecting the vapor liquid traffic data in the liquid having surface tension. And that is most important parameter when we are designing HETP by using Norton correlations, right? Norton correlation has some limitations, right? If you cannot use your viscosity greater than the 0.8 CP and surface tension is equal to 50 dyne. If you want to more viscosity and having more surface tension, you have to choose a rigorous distillation or other kind of software like KG Tower or Sulgol like that way. So they will guide you perfectly. And why we are performing rigorous distillation column, we will take the vapor liquid data of each tray, right? And we can put it into the KG Tower and Sulgol. So they will identify us what is HTTP, right? And what will be the diameter across the delta P. Because the delta P is most important parameter. If it is delta P changes, condition will be changed. If it is condition will be changed, partial pressure will shift. Partial pressure will shift, so alpha will change. If it is alpha will change, so separation will change. Right? So each and every parameter are linked with each other, right? We have to maintain the guidelines. No doubt, if we have a margin, have a 2 to 3% that will be deviated, that is okay. But that should be a fix. That should not be if you have suppose designed the delta P according to the 10 PSI and your delta P will increase from 10 to 12 or 14. So operating condition will be changed, right? So that's why we require rigorous column distillations, each tray of the sections, and the sections will give us each data like vapor liquid traffic data. And each of vapor liquid traffic data will give us efficiency. So we apply a Morphy efficiency law when we are performing into the rating mode. So distillation column automatically calculate into the rating mode as per their database. But practically, if you know the column efficiency. So you can put it over there. So simulation will predict total theoretical stage as per your efficiency. Okay. Other model is absorber. Like soluble component from the gas stream will have to be remove some gaseous or what I mean to say, we have to scrub it out. That will be used for the absorber. Right. Stripper, volatile component from the liquid stream, strip out from the system by using steam or generated vapors. Okay, that is the amine application, which is in amine regeneration and solvent recovery options. Then special column configure like reboiler absorber, reflux absorber, reboiler stripper, reflux stripper. All should be are the some specific model available into the Aspen Hysys. We'll see. I will show you into the Aspen Hysys. Okay. Some of the packings, I'll take only 1 or 2 slides. Otherwise, we have a 4 hours or 6 hours of the session, detailed session for the internals, and according to the how to review, how to check the data of into the kg tower. Okay, we'll perform the same thing because when we are taking separate course and separate session for the distillations, right, which is having 20 to 24 hours. In that case, we'll explain the how to check, how to review the kg tower data. Okay, and after running, how to check the results, what should be optimizations and solution for that. Here, generally, we know the train packings are there. Various kinds of packing and tray packings are there, and then pack column are there. In the pack column, having random packing, structure packings, how it will be performed, what will be the HTTP for a different kind of what is packing area, wide fracture, everything is to be considered when we are designing tray and pack column. Here is a condenser type, reboiler type, right? Condenser, total condenser, partial condenser, right? Dot, according to the condenser configuration, will size the column. Same for the reboiler, kettle type reboiler, thermosiphon reboiler. Will perform, will generate the data, vaporization rates and everything according to the selection of the reboiler. Here we'll see how shortcut distillation will perform. In the majorly output, we can get it as we've seen in the discussion on number of theoretical stage, R minimum, feed location, and condenser duty. So FUG method will identify Prensky Underwood Gilliland equation and feed location. This will be identify and calculate the as per the requirement and minimum or stages required to separate out the material. Okay. Here is the same. This one is the rigorous distillation column. How it will be identified, we'll take it one example for the conceptually how generally we size, what is the parameter to select into the monitor, right? What are the details we require to size? That is the most important thing. Here is some comparisons of the shortcut and rigorous distillation column. The bases are there like FUG, analytical matter, empirical method. And rigorous matrix, Newton-Raphson methods are using. Generally, we have studied into the engineering degree, third semester or fourth semester. So this method will be used when we are performing rigorous distillation column. Inputs required, light key component, heavy key component, right? Pressure. And after performing shortcut distillation, we are putting into the rigorous distillation column, stage-wise count, feed location, reflux, and specific targets and everything. Okay. And output will receive from the shortcut distillation is minimum stage, minimum reflux ratio, temperature estimation, even duty, right? Even we can get it flow rate, mass flow rate from the column, top and bottom as well. But in the rigorous, we can get it exact tray by tray data for the temperature, pressure, flow, everything, density, viscosity, everything. We can get it through thermal duties into the rigorous distillation column. right? Accuracy, low to moderate, extremely high rigorous distillation. We can get it. Basically, thermodynamically robust system, we can design it. Okay. If you are matching the shortcut distillation and rigorous distillation, we can see the ranges 70 to 80% of the changes you can see into the rigorous distillation column. But if you want to run these rigorous distillation column, you have to take some details, some data from the distillation column, and then you have to optimize by taking this data and putting into the rigorous distillation column, and you can optimize it according to your requirement. Okay. Same for a absorber. If you can see here is a lean liquid. Liquid is sent it from the top. Gas are sent it from the bottom. Gas has a tendency from bottom to top, and liquid has a tendency from top to bottom. And whatever the scrubbing and if you can see here, packings are when we select the packings and dia, that should have some velocity range and some residence time between the vapor and liquid. Here we need a maximum contact between the vapor and liquid. Then and then absorption will be possible, right? And that will be maximum traveling will be when it is possible when you are giving the maximum residence time. When it is possible maximum residence time, you have to select appropriate packing options, right? Appropriate data of diameter and total traveling time from total length of the pack column. That should be very important, right? In the packing, having the issues include the channeling, right? We'll see the detailed sessions of the what is channeling, how to avoid, right? If you have a suppose requirement is 10 meter of the pack bed. So we are not using the single pack bed as a 10 meter. We have to divide into the 2.5, 3, 4, 5. What is the criteria to dividing into the packings? Then we can put it into the what we can say liquid distributor. Liquid distributor will collect all the material from the top packing and then distribute it to avoid the channeling. What is the requirement and criteria to design the absorber stripping section? That is the most important parameter. Okay. Distill the absorber designing, it's not a what I mean to say difficult task. But when you are performing, when you are selecting the liquid distributor between the two pack beds, type of pack beds, size of the pack beds, right? That is the most important parameter. What is HETP? Right? Generally, when we define the total height, we have a two equation, NTU, number of transfer unit, and HTU. That will be define the height, right? That is the most important between the when we are mass transfer between the vapor and liquid, and that we have to identify, right? We'll take it in the detailed sessions for the absorber and stripper. These are the some other options, some features, purpose, and typical applications, right? Where to reboiler absorber, generally application, NG recovery, cryogenic plant, reflux absorber, gas sweeting, and hydrocarbon recovery. Reboiler stripper use amine regeneration and solvent recovery. Reflux stripper, petrochemical and solvent regeneration units. This is the some basic identification and basic implementations of the other kind of model into the absorptions and absorber and stripper sections. Okay. Now, how Hysys distillation modeling workflow? First, I told you field characterizations. Apply the input into the stream. Then select the component. Right? This is the first step. Second step, identify the best property package. You have to search according to your requirement, what industry using thermodynamic properties. Like suppose if we are using isopropyl alcohol and water, we need to separate. Some of the licenses are like Thyssen Group using NRTL, RK. Technical using NRTL, SK, right? If you are selecting NRTL, so differences between selection of thermodynamic property can changes the data. Might be 1%, 2%. I have seen a 3%, 4%. Okay. So you have to be a Google or check GPT. What will be there? You will get the different kind of companies using different kind of thermodynamic property according to their experience, right? So I'm not saying that which is the right option, but obviously you have to choose NRTL for if you are isopropyl water separations are going on. If you are choosing Peng Robinson, that will not help you. But NRDL series like NRDL RK, SK, right? That will be the okay because result will changes only 2 to 3%. Then column model selections. Which kind of column model you are selecting? Okay. Then performance analysis. After the putting the data, you should know the things how to check the analysis. What will be the temperature in your mind and in your concept which is having a like a garbage. Obviously, output you have received a garbage. Right input will receive the right output, right? So concept you have to clear with your concept, right? If you are good in the concept, you are good into the distillation column conceptually, definitely you will get the around 95 to 98, 99% right answer. First, perform a rigorous shortcut distillation, then perform rigorous distillation. Okay. Shortcut distillation, as I told you, they can give you the N minimum, reflux, some of the duties, some of the flows. Okay. Minimum reflux ratio, maximum reflux ratio, what you can optimize it and you can get it. According to your selected reflux ratio based on R minimum, you will get the exact and actual theoretical stage. You can put it those details into the rigorous distillation column. Okay, after rigorous distillation column, you should optimize and final design. One in between the optimization and final design, one more step is KG tower. Use a KG tower or Sulcol, or if you are using a Aspen Hysys for the same, right? So you have to do the rating or internal rating. That we have a separate 4 hour session in a detailed distillation column design. So what type of tray we are using, how to rating in distillation column. Okay. So this is the main task after the performing these activity. This activity can perform anyone else. That is not the issue. Okay. You can you can follow the step-by-step process. You can optimize it. You can freeze the distillation column, right? But after going into optimization and final design in between the selection of the tray, packing, number of passes, dia, flooding, trap flooding, okay, then deaerating factors, okay, distance between two trays, packing, type of packing, size of packing, void fractions, all the terms are used, right? So that will be very critical. You need some more time. If you can design a distillation column, you can size this distillation column by performing this task will require only 2 to 4 hours. But this task will take you at least 6 to 7 days to freeze your column, right? Because various options are available, various activity designing guidelines, and if we conceptually we have to follow. Okay, so optimization and final design in between, we have some selection of the tray, ratings, and everything are very important factor when we are performing this task. Now, again, we are taking one example into these simulations. Okay, what is the how to size the column into the uh, distillation column sizing. Okay, so first we'll take one example. Okay, first we'll size the how to size shortcut distillation column and how to size rigorous distillation column. Right, I will take one example. Okay, uh, 1 second. Okay, here if you can see 50% propane and 50% propylene. Right, here is some pressures and flow rates and everything is available. Now this is you can what you can do, you can perform these tasks from homework Okay, let's take it this one. Please, Jatin is allowed to perform to get these kind of PPT, or otherwise you can take a screenshot. I will take a different distillation examples to solve it out. This one is very easy. Okay, so first we'll select the case. Okay, so first this is we have a separate 30-40 hour session of the Aspen Plus as well as Aspen Hysys course, right? So I'll not go in depth mode, okay, how to select and what is this fundamentals and everything else. I'll start directly from the example because we are learning the distillation column. Okay, so I'll take here is a methanol, then water. These two components are there, right? Go for the property package. Now add a property package. Okay, so whenever you are selecting property package, that should be a right? If I can select anyone, so they will give a command to us, or if it is okay. Now Peng Robinson is one, but as per your chemical engineering knowledge, you should know NRTL or extended NRTL is the best option when we are performing any kind of nol component like ethanol, methanol, isopropyl alcohol, pentanol, and everything, right? Or any kind of which is not a hydrocarbon, which is chemical, right? So we'll use the NRTL, Uniquec, Unifac, Wilson. If you are using acid component like H2SO4 separation, acetic acid separation, we'll go with the acidic concept, right? So, or electrolyte NRTL, which is that property is not available in the ICs, but that should be in the Aspen Plus. Right? We'll select here extended NRTL as of now and go into the simulation part. Now, the simulation, first we need to select the stream condition, right? Now, Aspen Hysys is allowed to run a single stream condition too, right? Suppose if I can take here, go into the concept mode, we have to put here a data like a mass fraction or mole fraction, whatever you want to. Here I would like to say here is a 0.6 is my methanol and 0.4 is the water. First, we need to identify the compositions, right? Make a habit to put by your own experience or by own comfortability. Generally, I put it here a composition first. Okay, then go with the feed condition like 1.1 bar as an inlet to distillation column. Okay. Before going to selections of the how to size the distillation column, we have to identify some inlet condition of the temperature, inlet condition of the pressure, and how to identify the operating condition of your distillation column top and bottom. That should be a task which is available into the, if you can buy our course, so we can give us idea about which conceptually how to check the azeotrope and everything should be available in that one. Okay, so I am not going in that uh, function to select the boiling point and operating conditions and everything else. Right here, I will take it directly example. So my inlet feed is say 25 degree, right? And I'll keep it flow here, say 20,000 kg per hour. The Aspen Hysys will run, and if it is green with OK, right? So all the data have been put in right path, rightly, and whatever we can get the details, which is a right. Okay, you can see the property here and compositions are available here. Okay, then uh, okay, so all the details you can see. Performance we are performing 1 second. Compositions. Here we have put it wrong, 0.6 and 0.4. Okay, now we can get it here 0.6, 0.4, and these are the property. You need to check that twice, okay, before going to go ahead for the further operations or further distillation or any kind of operation, right? Because details are most important. Okay, now the system is okay. Now go into the separator. Here is the various kind of models are available. First thing is separator, vapor liquid separator. Then is the three-phase separator. This is the tank are there. Here is a rigorous distillation column. Here is a component splitter. Right? As we discussed, reboiler absorber, reflux absorber, reboiler absorber. Right? Here is the three-phase distillation, shortcut distillation, and refining shortcut column like ADU, VDU. Okay. Then liquid extractors are there. Three stripper could, then four stripper could, then vacuum rise tower, FCCU main fractionator, fluidized catalytic cracker unit, right? Solid separators, then other kind of separators are there. Okay. We can take this example by choosing a shortcut distillation column, right? In Aspen Hysys, we do not want to separate out the system. Automatically, the column, if you can put or if you can name it, automatically the simulation will generate the stream. Okay. Suppose if I can put here one stream, automatically will connect. Now I don't have any other stream to add. I'll just write it down the Q condenser. If you can see here, automatically will generate the stream. Then distillate. Then Q reboiler. Then bottom. Make sure number duplicacy should not be happen. If it is number duplicacy is there, simulation will not allow you. Like suppose if I can check Q R E B O, right? Here is a two time both the name are the same. So they will not allow you. They will take you directly bottom, whatever previously, or they will give you the alarming indication. So whatever you have selected, the naming are duplicacy. Second. Okay. So you can also check by using cursor and mouse out. You can also do. Okay. Now go into the column. In the column, first thing is go into the parameter. So these parameter can help us to light key in bottom, heavy key in distillate. Means whatever methanol, we know methanol is a light key and water is a heavy key. So they will ask a methanol at the bottom with water. And again, second option is water with methanol at the top. Our top requirement is methanol, but some of the water content is also applicable are there. So now we have to select here a methanol at the bottom and water component as a heavy key into the distillate. So now you can apply here mole fractions. I'll say 0.0.1, very less amount, and same water at the distillate with less amount. Now, as I told you, operating column and reboiler pressure is very important parameter to select before going to distillation. We should identify thermodynamically whatever we have selected thermodynamic component. We need to check what will be the condenser and reboiler pressure to separate out my distillation from the column, like temperature as well as pressure. Right here will not be provided temperature. We can give us the temperature here like 1.1, which is little bit more pressure, or if you can say 1.05 bar. And then you can also apply 1.2 or 1.3 bar because the pressure is higher than the condenser pressure, right? We need to have a delta T across the column. You cannot select both the pressure are same. Okay, we have some losses from bottom to top. We are choosing a tray packing that will have some pressure drop across the column, and that should be considered by taking the experience or by taking the conditions. You need to take care. Suppose if you are having a 60 theoretical stage and if you are providing only 0.2 atmosphere pressure drop, right? So whenever pressure drop is low, at that time diameter will be the higher. I think you should know the concept of the Hazy-Poisson equation. Delta P is equal to 4FL square by 2GD. So delta P is inversely proportional to the dia. Dia increases, delta P decreases. Dia decreases, delta P increases. So both options should be both are independent to the each other. Okay, and that is the more important. You need to check, right? Then here already I can get the reflux ratio, what I have specified the function, which is 0.709 minimum reflux ratio. So what is the actual or reflux ratio? So as I told you that, right, R actual reflux actual is equal to 1.2 to 1.5 time of R minimum. So here 1.2 into 0.705. Right? So I consider here as a 7 to 14 means 0.85, right? Or you can say 84. Now the column has been run, right? So various connections are there. Rating you will not get. Here you get a worksheet. What will be the distillations? What will be the bottom product? What will be the operating conditions, and everything has to be there. What is the compositions as whatever we have specified. We can get the distillation from the top. We can get the specified composition from the bottom. And we can get the other thermodynamic properties, what we have selected. Okay, physical, chemical properties into the from properties. And this is the main chart for us to select. Okay, so this is the main concept. This is our motto to perform the distillation column. So we'll take this screenshot first whenever we are moving ahead to the for rigorous column. So I will take here for screenshot and save as in the place. Okay. So here we can get a minimum number of stages is 6.69 around, and actual number of stage 17.48, or we shall consider here the 15. Okay, there are 18. Then feed location is 9. Condenser temperature, reboiler temperature. Okay, then rectifying vapor, liquid. Here is a duty. Everything is to be available here. Okay, so we should take care whenever we are performing. So that is our requirement that we need to take the snapshot. After this detail, you will not getting any kind of details from apart from the system, right? Distillation column, shortcut distillation having some limitation will be work based on the FUG method, French-Key Underwood Gilliland equations, right? So we have a limited data. Software will generate, or any kind of software in the market will generate limited data like this. Okay, they will not give you a tray on like that way. Okay, so now we can go into the rigorous column for the sizing. Okay, go into the view, take a model palette, then going for the separator one. This is the distillation column. Okay, I copy this string, paste it here. I'll ask to take the same downstream stream for the one. This is my requirement. Okay. The same data will be absorbed from the any kind of, if you want to take any string, you can copy paste and you can ask to user define from the stream. They will collect any kind of stream from here. Okay. Okay. Then ask, here is the main faceplate for the rigorous column. Same you have to identify 1-2. This is the inlet. Now, what we have done previously, we have simulated this data, right? And we have taken the screenshot. Okay, I'm closing this one as of now. I'll check these details. Right, total tray is 18. Feed location is 9. Okay, And whenever before the run the simulation, we have considered some reflux ratio 0.84. And also we know about the top temperature, bottom temperature. Okay, so first we can make a sketch. Q condenser for column 2, right? You have to tell the name. Now here is a total condenser, partial condenser, full reflux, various conditions are there. So we should know which kind of column is this. If it is propane propylene like this, right? So in this case, here is a sum they will consider as a partial condenser. Okay. So partial condenser will identify you to the some of the conditions, take it from the top, some of from the distillate, whatever condense is there. Okay. So here you can see now consider as a total condenser, right? As put the name methanol on distillate. Okay. Same. They will simulation will automatically generate the stream, right? Q reboiler column 2. Okay. Then we know here from the water from bottom, right? After putting this kind of detail, they will ask you the feed location theoretical stage. So what is our theoretical stage? 18. Theoretical stage. What will be the our feed location? Feed location which is having a 9 stage. Okay, from the shortcut distillation. I have taken those data from the shortcut distillation to stages and 9. This is the preliminary data. Okay, you have to identify or recheck to optimize as per your requirement. Efficiency, FUG method will not be considered efficiency, but rigorous distillation, we have to provide the efficiency from practical experience as well as some of the literature data, right? You have to consider for morphic equations or tray-to-tray efficiency equations and all. And that we need to put. I'm not saying simulation is 100% right. Practical approach is also important when we are selecting the efficiency, right? If you selected efficiency 0.7%, only 70%, right? And when you are performing and when we actually practically efficiency, we get only 35% or 30%, right? So your theoretical stage would be double. So you need to take care. You have to cross check twice, thrice for existing plant or some of the practical approach or some of the calculation. You have to take all the collaboratively and then you should check. Then here is a option to select a reboiler configuration, right? Or once through circulation without baffle, circulating with baffle, rigorous Hysys reboiler, heater, heat exchangers. So most of the options are available. Our purpose is to optimize the distillation column designs, reboiler duties and all. Here we are not going to check circulating baffles and everything else. This is the I am talking about when we performing distillation design. In the first stage, we call the FEL1, front-end loading 1. This is the initial stage. Then we go with the FEL2, means front-end loading. We'll check again rigorously. Then we do the design, feed conceptually, and then we'll fix it. Various stages are there when we are performing the distillation. In the first, conceptually, you cannot identify or select or assume that whatever you have selected, that is right. Right? You have to optimize multiple times. Then going the next one, right? This is the condenser pressure, reboiler pressure, what we have selected previously. Okay, and that should be a fixed one that we need to take care and when we have to put into the, when we are optimizing the column. Okay, so previously what we have considered a column pressure is 1.1. So we have to put 1.1. Okay, then reboiler pressure is, we have to consider 1.3. 0.2 delta P is most important thing when we are performing the task. Right? We know that the condition, what we are selecting, keep in your mind, because that is the engineering experience. You have to apply your knowledge, right? According to your requirement. Suppose if you have 100 stage, so you cannot say that like only, okay, I have only this much pressure drop I have. So you have to change the conditions, because we have some certain mechanical point of view integrity or some mechanical point of view concept, because traveling liquids and vapors depending upon the load, right? That should be also considered. Then after selecting 1.3, go next. Do not put anything else here. Optionals are there, temperature, pressure, bottom estimation, and everything else, right? Then liquid rate, reflux ratio. All the importance are, if you want to put reflux ratio by considering the shortcut distillation bed, that is also okay. If you are not putting the details, right? If you want to check what will be the reflux ratio as per your requirement, whatever you want it, right? So skip it, right? Then check the done, right? Now after putting the conditions, they will open like this. Okay. So opening this kind of faceplate means you have put it whatever details you have, right? And what details you want it, that you have to go into the monitor, right? In the monitor, they will give us, or we have to specify some information to get the details. Okay. Okay. So reflux ratio, distillation rate, reflux rate, bottom product rate, all those are the options. Now, if you want to add more options, you can go add specs. Now, what is our requirement? What we have to target in the distillation column? Why we are using distillation? We want separation from the mixture. So ask the component, fraction component, what details you want it, right? So here we can get it, a composition fractions. At what composition fraction, at what stage you want. So you have to specify something else like condenser. You want condenser at mass fraction at the liquid after condensation. What product or material you want? I want methanol, which is having a 0.999 purification, means 99.9. Start it from 99.5. Okay. Then you can increase it. Okay. Then first specification we have specified, right? We have to now here a degree of freedom is 0, right? You have to choose any two options, right? Option is activations. Select first one. Composition, our is a main requirement, 99.5 is a methanol. Okay. Compositions, fractions is a most important requirement, 99.5 methanol. We want it from the top that we have to select. Now again, here is a, they will ask any other input to provide degree of freedom. Okay. So actually I have something else. So you can put it from the shortcut method. So what shortcut method we have those details, you can take it from here, anything else. You can take it, copy it, reboiler duty, copy it, go into the rigorous distillation column. Okay. You can ask monitor, add specs, or you should ask a duty. Duty add specs. Okay. Which duty you want? Reboiler duty or condenser duty? We have selected reboiler duty, and you can put it the paste the value here. That any other we have degree of freedom is 0. Now reset it and run the column. Now column is run, right? Rigorously. Now what reflux we have considered previously? 0.7. As per the 99.5% composition, what theoretical stage we have required 1.453 as a reflux ratio to get this kind of purity by applying this duty. You can also provide a bottom temperature. You should also fix the top temperature as per the rigorous distillation column, but you should not 100% rely on the column or FUG column to get those details and put it here. Because main motto, I want something purity that I want it to freeze it out. Okay. So I can also change my requirement 99.9%. Okay, check. My reflex ratio has been increased from 1.25 to 3.23. So whenever you are increasing the fractions, right, at that time, your purity or reflex ratio increases. Suppose if you are thinking, I can increase the theoretical stage, definitely you can increase, right? You can go like a 25, keep it internal stage is same, right? Go into the monitor, reset it, rerun. Look, 1.8. After certain time, you have to fix your requirement like options like A, right? Go into the monitor options, reset and rerun. 1.526 to get the composition fractions 99.9. Now you have to choose whatever I am increasing the height, what extent should I select, right? Because feed location, everything is to be important when we are selecting. After certain time, the result will not be changed. Result will change it, definitely will change, but certain limitations. Okay, after certain limitations, they will change into the some minor changes. Suppose if you can select 35 stages, 1.35 year is your reflux, right? Now I am converting into the 40. Now you can check here. Run 1.24. So whenever you are increasing the theoretical stage, reflux will be changed, but you should check how much percentage differences are there, right? Don't think like if I can change if I can change converting into the 100 theoretical stage, so I don't want to be a reflux. No, do not consider those concepts when we are performing the distillation column. Always certain has a limitation. Now 1.16, previously 1.24, right? Now again going into the 50, 1.16, convert the 50 theoretical stages. Then check. Previously 1.16, now 1.1. So you have to check what is the difference between the 1.16 minus 1.07. What will be the percentage benefit you will get? I think only 0.01, right? If after increasing the 5 theoretical stage, after a certain time, right? Simulation will give us same result. Okay. Now check if I can perform 55, right? Previously we have a 1.1. Now check 1.064. So 1.1, right? And 1.064. What is the percentage differences you have to check? So you have to check optimum theoretical stage, not less, not maximum. After certain time, you have to do the reflux, right? And second thing is in this case, some of the pressure drop, whatever we have selected. So this is the calculation. We know the whatever we have performed the calculations, right? There should be a some fraction of the pressure drop across the system, right? So we should make sure whenever we are designing, right? Pressure drop should be realistic, not the performing like a mathematical, right? 50 theoretical stage should not be done or should not be considered 0.2 atmosphere. Okay. 1 second. Huh? Okay. Actually, the server is not working over there. So first we can take some questions and queries from your side. So someone has asked what will be the happen if we specify more number of parameters. Look, degree of freedom is 2. If we can provide more than that, right, they will take it. But the result will be optimized according to that. If it is right or wrong or manipulated, that we don't know, right? So whatever software will ask the minimum requirement, you should provide only that much information only. You should not put more than that what they have, they don't want to, they don't have to ask you, right? Provide any two options as per your requirement, right? What is my practice? I will ask what distillation is for what? For separation. For what separation? I want methanol from top. So what percentage I want? I want 99.99%, right? That is my requirement. That's why we are performing distillation, right? So generally specify the component fraction from the top. Let them to define by the reflex or from the software only, right? Then you have to specify some of the thing like distillate rate. Okay. Then what I meant to say, bottom rate, distillate rate, top temperature, top pressure, bottom pressure, right? Yet you can play with that, right? But always you should ask the reflux because reflux increases your heat duty, right? Optimum heat duty you should know, right? I am not saying too much heat duty or lesser heat duty or higher heat duty. That is for benefit for you, but you should always choose optimum way. Second question, yeah, to converge, have to make sure DOF is zero means system is degree of freedom is zero means system is defined completely. Yes. So degree of freedom, whatever you specify, whatever input they want, they are already sufficient to run the simulation. And my suggestion is to you for you to only put what software want. Do not put extra information to confuse it. Over specified information will not be give you a perfect results. Okay. 1 second. What is the next question? People are asking the questions. 1 second. Define demand and product purchase, some of the software distillations. Where we are, where we are in certificate, 10 years property package. But we are in the next, wait a minute, along with top bottom. Outside, okay, the host said relative volatility is the ratio of partial pressure compatible ratio of saturation pressure or vapor pressure ratio. Actually, the PA partial pressure is a ratio of a two component, right? Benzene and toluene. So that should be a relative volatility. For top, bottom pressure and column pressure drop, we need feed stream inlet pressure as also define the flushing. I don't understand the question. What is your channel name? Not able to see the presentation. Okay. Real case studies for actually doing real case studies, which book to refer to how to do the simulation for real plant. You have to take it real plant from the real concept only. You can refer Jumana. Okay. Well, I think there is only one method to really work at process and equipment designing from who are good but cannot learn. Okay. What is the question after session? Shortcut distillation, is it possible to determine number of years? Shortcut distillation will give you the optimum reflux ratio, but that is not sure that you have to be perform and check as we have seen. If you can see, 1 second, let me in. Okay, so that is a depending upon the distillation column. That shortcut distillation column give us the some rough idea about the column basis. Those data you can put it into rigorous and then you can optimize it. That is the right way. Suppose some of the people don't know the initial what kind of information I have to put. Everyone, some of the people don't know, right? So rigorous distillation or a shortcut distillation gives us some basic information: temperature, pressure, reflux, relative volatility, etc. Number of theoretical stage, feed location, everything else. Then you can optimize it as per your experience and engineering knowledge. Okay. What criteria determine the uses of the total and partial and full reflux? Suppose in the distillation having a propane and benzene. Propane will not be condensed at what pressure we have, like atmospheric. Benzene will condense in atmospheric condition. So benzene will condense it, propane will not be condensed. So we have to select the partial condenser too, right? So partial condenser means some of the vapor will condense, some of the vapor will not be condensed according to the whatever temperature and pressure we have identified. And depending upon the end of product phase or non-condensing gases are having to vent those use paths. Okay. Not all time short. Not all time we need shortcut distillation. In some may project we have a directly do rigorous distillation as soon as my column is converged, then we will turn parameter of column so that our specification meet. We will work KG tower definitely, but general practice is at least we should know the what is the minimum requirement of the column, right? If you can directly perform rigorous distillation column, that is okay. But operating temperature, operating pressure will not be changed. So those data that can be identified. Then if you do not want to take it theoretical details like theoretical stage reflux ratio, okay, well, but at least you should take it from the flow rate data, right? Then temperature data from that, and you can put it. And this is a standard philosophy. The company person to person it may change. If some of the person can do the what I have follow the practice, at least still if you haven't knowledge about that product, that also you can perform those kind of activity to first perform the shortcut distillation, then go for the rigorous distillation. What is the specifier? Already we have discussed, and we can decrease the energy. Conversion optimum be negative, but it will be negative. The column will not become okay. We can decrease the energy. We are applying the vacuum. Why can't we apply vacuum and decrease the energy? Look, vacuum decrease your dia. Definitely you can use your vacuum. But when we are performing the vacuum distillations, you should know the criteria to perform. If your product is decomposition, then and then go you for the vacuum. Vacuum will decrease your system definitely, right? But is there your material decomposition mode? If it is not composition mode, if it is your atmospheric is okay, so why don't you go for the atmospheric distillation? And some of the cryogenic component, low volatile component, low boiling point component, you cannot go for the vacuum distillation. Vacuum distillation having some range, like suppose tetraglycine. Tetraglycine having a 260 degrees Celsius at atmosphere. So definitely I cannot choose the option of the atmospheric or the pressurized distillation column because PV is equal to energy, pressure increases, temperature increases, right? I'll choose a vacuum. I'll choose a vacuum 10 torrs. So my operating temperature should be 190 to 196. But we should take care. The material should not be decompositions mode, and that will be the requirement. If you are going for the if your boiling point is higher range, always we should select the vacuum. If you have three component, then I guess having the specified three parameter under the specs, right? Look, no. First thing is you have to check. Suppose if I have a three component benzene, toluene, xylene. I know that benzene is a lower boiling point. Toluene is the then again benzene has a 80.6 degree. Toluene has a 110, and xylene has a 135 to 40. So you should know. I want a top benzene and toluene, right? So you can ask the software to get the toluene. If you can get the toluene, then automatically you will get the benzene from the top, and you can separate out xylene from the bottom. Okay. If you have a side draw, so you can apply the side draw activity like I want benzene from the top and then from the side, I want toluene, then bottom from the xylene. Okay. What is optimum reflux ratio? 1.2 to 1.5 time of the optimum reflux ratio from the minimum reflux ratio. How to decide minimum reflux flow rate? Look, minimum reflux flow rate based on your purity of your compositions, right? Then we need to calculate what purity you want. According to that, they will give us a minimum flow rate. Then number of parameter to be specified depending upon the number of degree of freedom. Okay, okay. Vacuum can also lead to buckling and manual sharing. Does the shortcut distillation use multiple component? Definitely. Multiple component shortcut distillation you can use for the distillation, multiple distillation component. And how to put the packing for multi-cut distillation when the tower is tagged by the tray tower, and how to make the dimensions for making the tower height. Look, that we need to have a separate session for that, because that will have a huge and big task for you. KG tower is FUG? No, KG tower is for the column sizing. Internal packing sizing, you can consider, you can choose a packing from them. You can size, you can choose the delta P across the column by taking the packing or tray and everything else. They will give us, as per our hydraulic data, vapor liquid data, they will give us the column performance, how your column will perform. Okay. They will alarming you to have a optimum condition or optimum selection of your, what I mean to say, packing. Right? Delta P is a governing case. Flooding velocity, they will share us. They will also share us a downcomer, then jet flooding, everything. The case study, we have to see each and every parameter, each and every conditions of the like packing and tray should have two selection criteria. We have to select if we are tray type, if we are using a tray, if it is more than 2 to 3 meter, 4 meter, 5 meter diameter, we have to select number of passes. We have to increase the distance between two tray. So various criteria are there, and those criteria we can choose it from the KG tower. External reflex shortcut 1.2, yes, yes. So 1.2 minimum range, but we have a range 1.2 to 1.5. That is a theoretical range. Okay, you can increase it more than 1.5. Okay, to 2.53 like that way. That is up to you. Actually, I wanted to be starting the case, but the remote desktop and the Hysys software is not available because due to the tough, so I can't access the Aspen Hysys. Okay, now, okay, so you can check it here. So this is the composition fractions. Okay, screen is visible, guys. Okay. Okay, now the column is simulated. Okay, now whatever requirement we have achieved and whatever tray and whatever we have selected, tray field stream, everything has to be selected. Now, after the getting this information, that is okay. Now, what detail we wanted from this Aspen Hysys and what we can do it on, why we are taking the details from Hysys. So generally we can get it a performance parameter, column profile, go into the column profile, take those details, right? From mass fractions and everything else. Now these details will help us to put it into the KG tower, and this KG tower will actually perform your column by considering the internals, okay, like temperature, pressure and all. So if we are taking rating or if we are selecting the internals, so we have a two option to select the add new or auto selections, and let them to ask the auto selection by the software. Software will guide us what to do, or otherwise, if you have a good knowledge, so you can add your own way. So I will add a new. So I'll add a new. So they will consider only one case. Okay. If I will ask the auto selection for the software will guide us the right path. Means first to 23, 24 to 25. This is the diameter has been calculated by the software. 1.8 meter and one is the 1.8.47 meter. This is the trace spacing, number of passes, type of packings, right? Type of pack, columns and everything else. Sizing mode. Here is the interactive sizing. As of now, we are not going to be for the rating mode. Now, whatever you selected, that system is converged. But whenever, if we are talking about the internal calculation, it has a warning. So where has to be check the warning? You can check the warning from the hydraulic plots. So here they will show you the error. What is the error? Red means issue. Your column is failed. Green, whole sky blue will identify your column is running perfectly. And yellow, which is indicating both of the things. Column will run, but finding the issues in that case, right? So we do not want yellow or even red. So now you have to optimize your column, right? Need to change the parameter number of passes. You have to change the type of packing. You need to change the tray spacing. What is the requirement? What is the guideline for that, right? What is the number of passes requirement? After what diameter you have to choose a 2, what diameter you have to choose a 4, 6, 8, 10, 12. Up to the 12, you can choose the passes depending upon the diameter. If your diameter is 6, so you have to definitely 1 or 2 passes will not be work. At least you should have a 4 or 6 passes, right? What is the passes? How to select the passes? That we have a separate session for that. Okay, but just I wanted to highlight you. This is the passes. So liquid will receive from this downcomer and going into the place of the next tray of the downcomer. Okay, if you can select here a number of passes, a 2. So here the 2 time or 2 different places material will flow. If you can select a 4 passes, right? So 4 different places material will flow. So that is the requirement to select, but there should be some criteria to select 4 passes, 2 passes, trace spacing, right? Now, before going to passes and rating mode, first we have to run this case perfectly, like no error is generated in this simulation. Suppose if you want to remove the complete error, so you have multiple options. Play with tray spacing, play with dia, play with passes, play with tray, right? All those is the options. But packing, if you can change the packing, so packing has some limitations, right? So which kind of limitations are there? What up to the diameter we can choose the packing. There should have some requirement. Okay, you cannot choose a packing everywhere. If you have a 3 meter, 4 meter dia, so you cannot go with the packing. Packing certain has a limitations. Okay, operating conditions. If your operating pressure is 5 bar, 10 bar, 20 bar, packing will not be work. Definitely we have to choose a tray. Some of the diameter constraint, forming constraint, right? Solid constraint. So all those parameter have a selection of the tray and packing, right? Now I wanted to run this case by any without error free. So I'll increase the diameter, right? So I'll consider as a 1.9 here. And here is also 1.9. Internal input completed. So I have to make it both upper column and lower column diameter is the same. Now you check it. Now little bit is green. Sorry, sky blue. I wanted to just remove the yellow portion by changing the data. right? I can also increase some of the 1.95 dia or to optimize it. Now column is successfully without any issues or warning, right? So this kind of approach you have to perform, but this is the rigorous approach, right? Again, you have to optimize it by using the best knowledge. Okay. You have to also select or you have to also choose your pressure rating by optimizing geometrical parameter, design parameter. You can fix it like a percentage jet flooding, pressure drop across the column, and designing factor, forming factor, multiplier factor, where to use, when to use, right? So that is the main concept for the sizing of the column. So previously, whatever we have run, that is the only 50% of your column up to the selections of the shortcut sizings and then rigorous sizing. Then we have mitigating our flow rate requirement, top temperature, bottom pressure, temperature. Everything has to be fixed operating condition. Now main task is to size or to rate our column, right? That is the main task. Rating option is also there. After rating options, okay, they will give us some view, then check the performance results. Okay, here is the results, whatever we have identified, tray by tray options. Here we can get the tray spacing, section diameters, total height of the column, total pressure drop. If you can see 149.4 millibar, right? Then previously we have increases the dia and we have sorted out. So increasing the dia pressure drop should be pressure drop is the lesser than the what we are expecting, right? So diameter is a playing governing case, but this is the not right practice to increase the diameter. We have to choose the right uh, pressure drop across the column, lower pressure drop column, higher pressure drop column, both option should not be select. We need some optimum, what we can say, pressure drop. The optimum pressure drop should be between the 15 to 30 water column of the even tray we are using, if we are using pack column or any kind of. So 50 water column to 30 column is the right option to choose the pressure drop, right? Suppose if you have a 100 theoretical stage, we have selected 20 water column per theoretical stage. So total 100 into 20, so 2000 water column is my pressure drop. Suppose if I can convert it 2000 water column into the bar, so zero point 0.2 bar is my pressure drop across the column. But I can go with the zero point 0.3 for the best results, right? 0 0.4 that we need to check by using this case. So we have a certain limitation that we need to check. So that's what I'm trying to explain you. So whatever we are performing and whatever we are designing the column, right? We need whatever we are specifying, whatever we are designing by shortcut and putting and running the simulations, that is only 50% work. Rest need to be taken care by this activity only, the rating mode, selections of the tray, pack, right? Passes, tray spacing, right? Which kind of, suppose if you are performing amine distillation, right? So the forming factor is not the one. You should go with up to 0.65. If you are going 0.65, 0.7, so diameter again increases, right? So forming factor is also major part of your system. Then percentage jet flooding, right? That pressure drop, velocities. So these are the parameter we need to check. Okay. So due to time constraint, we have only performed the distillation column. Okay, so this is the distillation column, what I have explained. Otherwise, we have to perform some separate case. We need at least 4 to 6 hours for the, even we need some internal sizing too, or internal information too, to guide how to perform internal sizings and all. Okay, so I'll take question answering. Please, can you share the manual after the webinar? You should ask it from the team member. Why have you selected 55 stage where the number of stages suggested in the shortcut method is 18? It is just to reduce the reflux ratio. Obviously, because reflux ratio, which is a governing case to capex and opex. Capex is a not part of the system. Opex is the main condition because operating cost is 24 hours, 365 days, then up to the next 20 years, 25 years. Capex is the only issue in initial stage. OPEX is the issue for next 20, 30 years. So we have to focus on the OPEX, right? We'll cover it, whatever we have invested for the extra theoretical stages. How does the selecting wrong fluid package after your column calculated require duty? How does the selecting the wrong fluid package after your columns calculated require duty? Okay. I can't understand the question. Could you please provide recording? Please share your manual webinar. How we can apply the vacuum in the column. How can we apply vacuum in the column? Actually, you can just apply the vacuum in the column like just putting the operating conditions like minus. Right? Or you can say 10 torr. 10 torr or 760 mmHg. Here is the we have a torr. Okay. So here is the torr. So you can apply torr or you can also apply the putting the minus value. Okay. Minus indicate the vacuum. And it's package during the training concept. Could you please provide? Okay. Can you share the related email connecting with you? How to hydraulically obtain efficiency of trays? How to hydraulically obtain efficiency of tray? Or the method mine is exporting to the KG tower, then receiving the efficiency and optimizing my tower. I will do it until the convergence of the efficiency. And am I correct? Look, efficiency is a different thing and KG tower concept is a different thing. Efficiency will give us the actual practical data, right? Because what happened? Efficiency depending upon the trial and error based on the experience. If you can go with the BTX, benzene, toluene, xylene, theoretical calculation or a theoretical approach, they will show you only 50 to 60 theoretical stage. If you can still consider a 50% efficiency, they will show you a 110 theoretical stage. But if you go and ask the UOP licenser, Universal Oil Production Licenser, which is the licenser of the BTX, so they suggested 180 stages, means efficiency is only 30%, right? So I am not saying about the efficiency selected right or wrong and Morphy efficiency and tray by tray efficiency right or wrong. There should be having some practical approach, right? If you are developing a new product, if you are working on the new product, so you should have a lab trial. You should have to take the lab trial in the lab. You should have to develop some lab model into the, then you can take those data and then you can implement it actual efficiency. Okay, this is the options. Why high pressure packing is not good? Because packing has some limitation of the design pressure. Packing will design based on 3.5 bar gauge or 5 bar gauge, right? Now, if you are choosing 10 bar gauge, how the packing will act? If you can increase the thickness of the packing, right? But your dia is also increases, weight is also increases, right? Everything is increases. So ultimately will affect on the cost. Understood? So generally we are not preferring packing for the higher pressure. Why need a shortcut distillation if we opt a rigorous option first? Definitely you can choose it. That is not the issue. But you have to do a trial and error basis, right? And I'm not interested to develop the trial and error basis. I'll choose a first distillation. I'll take some basic information, basic data from them, and then I'll put it into the rigorous column. Definitely, you have to optimize your column, but that iteration and trial and error basis will reduce. So your time will reduce. In industry, which type of mold tray or pack, depending upon the component and requirement. Okay, I'm not saying specifically. Everything has the depending upon the which service you are selecting or following. Hello, will our recording have we calculated HTTP in the simulation activity? Look, already we have calculated, right? In the rating or internal mode, right? We automatically has been shared or calculated by the software. If you can see the rating, internal sizing here are developed by the trace spacing by the software. So you can choose it by your own way if you want to, suppose in the range. Okay, now you can check into inch 0.609 meter, right? Around 24 inch it might be. Let me check. 24 inch. Right, this is a 24 inch. You want to change as per the dia 30 inch, you can definitely you can choose 30 inch, right? But you have to check the pressure drop across the system vapor liquid traffic. When you are performing, when you are selecting the trace spacing, that will take its separate session. The trace spacing, why we choose, when to choose trace spacing, at what dia, at what conditions, same for the passes, same for the packing, right? Everywhere, why we are choosing a C, when we are choosing a CU plate, bubble cap tray, right? Then wall tray. These are the some options available, right? So that is the criteria. Again, only attendees shown. Only attendee show the on the screen. How can I determine the space between the tray? There should be a guideline. You cannot specify the tray spacing randomly. There is some guideline. Okay. So those guidelines need to be checked according to the vapor liquid traffic, vapor load, liquid load are there. I am not saying specifically, but there should be a 18 inch, 24 inch, 30 inch like way. Which one is the more important, column diameter or length? Both should have their depending column dia and height. Both are important. Height for the purification, dia for the flow rate and pressure drop across the system and operating conditions. The rating mode, any correction by software, the top and bottom pressure against the shortcut distillation input. In the rating mode, any correction by the software, the top and bottom pressure against the shortcut distillation will not show you the rating mode. Rating mode only you can specify in the rigorous distillation column. And the rigorous distillation column, before going to rigorous distillation column, you have to fix the operating condition like temperature, pressure for both top and bottom. Okay. Distillation column effect that depends upon which factor, various kind of factor, like uh, first is your material, compatibility material, like acidic material, like solvent, operating pressures, operating temperature, dia, height, everything type of selection of the pressure or a packing's height, tray, right? If you are selecting packing 250, 350, 450 also impacted on the column efficiency and all. Okay. Okay. I think Q line is depending upon the feed inlet conditions, right? Q is the feed inlet. We have a total 5 kind of feed, right? Which we can consider when we are designing the distillation column. Q is also important, like subcooled liquid, saturate liquid, then partially liquid, partially vapor, then totally liquid, totally vapor, totally superheated vapor. Suppose your boiling point of benzene is 80, but you have been operated 110 degree. So 110 degree is the saturated vapor for the benzene, right? So that will be the Q line, and Q line is important when we are designing the column, because Q line is also effect on the feed location, total height, duty of the condenser, duty of the reboiler, and most of the thing. Can I give the efficiency by my own way? Definitely, but you should know, right? You have to take the help of Google, Chat GPT, practical experience, running plant. You cannot put the efficiency like randomly, right? Okay. Okay. Uh, Ritu and Jatin, now you take it further.
Yeah.
Yeah.
Thanks for today's webinar and giving us the most important and experience insight on how to develop the distillation column design. Also, we have shared the feedback form for all the attendees who attended the webinar today. We request you all to please give us your valuable feedback on the on the webinars insights. Also, we request you to follow us on our different channels that we are having, like YouTube, Instagram, and WhatsApp channel. We'll share our community channel in this chat box only. You can get the insights on different trainings that we are providing. Also, we'll share our contact number in case you have any doubts regarding today's webinar. Yeah. So again, thanking you all for giving an a, a time of yours for today's webinar. We also thank our trainer who gave us good insights on the topic and gave the justice to the topic. Yep. Thank you. Thank you all for joining.